Hello students. So now this is a practice time. We came here with the practice time 1 session of the chapter moving charges and magnetism for the year 2023-24. Now after this session, you are able to understand the concept like how to apply the numerical, how to apply the formula in a particular question, key principles and practical application. What is the meaning of a practical application here? Like after the particular question, you will be understand what is the final result will be comes from that particular part. So let's begin with the first question which we have. Magnetic line of force due to a straight conductor carrying current are straight line, elliptical, circular and parabolic. So in a simple way, if I'm just taking a straight conductor, I hope you are able to get my particular answer. Like if I'm just taking a conductor which actually flowing the current, so the direction of a current we can easily say that is a what. If I'm just taking like right hand rule, okay, from the right hand rule we can actually use the direction of magnetic field lines, that will be circular. Okay, are you able to give the answer like a clockwise or anti-clockwise? Just try to tell. What is the direction of this? This will be clockwise or anti-clockwise? Yes, this will be clockwise. So the answer for this question is actually circular. Next we have a magnetic field exert no force on a stream of electrons, a stream of proton, unmagnetized piece of iron, stationary charges. The answer of this question is a stationary charges. Because if I'm just taking a stationary charge, so for a stationary charge, they have only electric field lines. I hope in the first chapter you have studied about the topic electrostatic. And in the electrostatic, that is a part of the charges when charges are in rest. That means stationary. So as its name clear, electro, something which is related to the electricity or the charges, and static means rest. Understood? So a static charge or a stationary charge produces actually electric field lines or creating electric field lines only. Next question we have a current carrying power line carrying current from west to east. The direction of magnetic field 1 meter above is north to south, south to north, east to west, west to east. The correct answer for this question is a north to south. Next question we have. Among the following, one is incorrect. In the case of a straight conductor, carry conductor, we have these particular graphs. Now, among all these options, one is incorrect. So firstly, we have to understand what is like what formula actually related with this. So as in all the diagram, as you can see over there, we have a different kind of a graphs. Now, magnetic field due to a straight wire carrying current which is I, for that formula which we know, that is a B is equals to mu naught I divided by 4 pi r. In terms of a cos theta, so we just take the value of integration term. So the result finally which comes in the sine form, that is the sine phi 1 plus sine phi 2. I'm just making the diagram for more clarity. If this will be the rod, if at point particular P we have to calculate the magnetic field, the value of a B. So for that scenario, it will be make an angle theta phi 1 and phi 2. This will be, I'm assuming this will be actually phi 1 and this will be phi 2. So for this scenario, the result will be comes in this form. So as we can see, B is directly proportional to I, B is inversely proportional to R. As all the graphs, we can see over there B and I relation. In the first one, And in the fourth one and the second and the last. So as we can see, B is directly proportional to the I. So for that scenario, the graph should be in a straight line graph, because that proportionality will be showing the actually simple that if we increase the current, magnetic field lines are increased, or the strength of magnetic field increases. But actually the diagram which is showing here, that is a completely different. So the wrong answer will be actually 4. Moving ahead with the next question, cosmic rays are said to be highly energetic protons hitting the earth on account of earth magnetic field. They should get deflected too. So north, south, east or west. Student, the correct answer for this question is the east direction. Moving ahead, cyclotron is a device which is used to produce high magnetic field, high electric field, high speed electrons and high speed ions. The correct answer for this question is option 4, that is a high speed ions. Moving ahead, next question we have, the figure shows a uniform magnetic field P directed to the left and a wire carrying a current into the page. The magnetic force acting on the wire is towards the top of the page, towards the bottom of the page, towards the left, towards the right. So the correct answer for this question is, like this is the diagram, and from this diagram we can easily clear the answer, which is towards the top of the page. Clear? Now, next question we have, a current carrying wire produces in the neighborhood electric and magnetic field, electric field only, magnetic field only, no field. So the correct answer for this question is magnetic field only. Like if I'm just taking a current carrying wire in a neighborhood, it will be carrying only magnetic fields. If a long hollow copper wire carrying current, then magnetic field produces will be inside the pipe only, outside the pipe only, neither inside nor outside, both inside and outside the pipe. So student, as we know from the basic knowledge, inside the conductor, the value of electric field will be 0. But if I'm just taking, this will be situation for the only when the charges are in the rest. But if the charges are moving, the correct answer for this question is outside the pipe. Okay? Means inside magnetic field lines will be also 0. Magnetic field at a point on the line of a current carrying conductor is maximum, infinity, 0 or finite value. The answer of this question is 0. Next question we have, the magnetic field due to a current element is independent of a current through it, distance from it, its length, nature of material. Answer is the nature of material. Next question we have, the direction of magnetic field produced product of a linear current is given by. Again, I am repeating the question. The direction of a magnetic field product of a linear current is given by right hand thumb rule, Fleming's left hand rule, Joule's law, Ampere's law. So direction of magnetic field actually we are taking from the Fleming's left hand rule. Next, a current I flows along an infinitely long straight conductor. If R is the perpendicular distance of the point from a middle of the conductor, then the magnetic induction B is given by. We have these formulas. So the correct answer for this question is option 1, which is P is equals to mu naught by 4 pi 2I by R, where mu naught is the what? Permeability of free space. Mu naught is permeability of free space. The value of a mu naught, that is a 4 pi 10 to the power minus 7, that is in Newton per ampere square. So moving ahead with the next question. Two very thin metallic wire placed along x and y axis carrying equal current as shown AB and CD are lines at 45 degree with the axis having at origin O. The magnetic field will be 0 and the line. So as you can see over there, there is a point of a junction. Okay, so we have to actually calculate what is over there, what is the actually value of x and y lines. Like so we have these particular options AB. The question is like AB and CD are lines which is a light at 45 degree with the axis having origin. So the magnetic field will be 0 and like on the line. So magnetic field where it will be 0, we have to calculate that particular line. AB, CD, straight segment OB, only of line AB, straight segment OC, only of line CD. So the correct answer for this question is AB. Okay, because as you can see, there will be the no current which is a pass through here. Moving ahead with the next question. A vertically straight conductor carries a current vertically upward. A point P lies to the east of its a small distance and another point Q lies to the west at the same distance. The magnetic field at P is, we have these options. Greater than at Q, same as at Q, less than at Q, greater or less than at Q depending on the strength of the current. So the correct answer for this question is greater than at Q. Moving ahead, we'll have a next question. For a given distance from a current element, the magnetic induction is a maximum at an angle measured with the respect to axis of the current. 3 pi by 4, pi by 4, pi by 2, 2 by pi. So the correct answer is a pi by 2. Next, we have a question. The magnetic field vector dV due to a small current element dl at a distance small r and carrying current I is. We have these options. And the correct answer for this question is option 4. Now, the next we have a straight conductor carrying current I is split up as shown in the figure. The radius of the circular loop is R. The magnetic induction at O is equals to, so 0, mu naught I by 2 pi, mu naught I by 4R, mu naught I by R. The second we have an option mu naught I by 2R. So for a circular loop, the correct answer will be 0. Okay. Next we have for a solenoid of length L having n turns given by, we have these formulas in which we have to select the right one. So the right one is first mu naught Ni by 2L cos theta 1 minus cos theta 2 in the term of a solenoid if they have n turns. Next we have a uniform magnetic field is directed into the page. A charged particle moving in the plane of the page follows a clockwise spiral of decreasing radius as shown. A reasonable explanation is, we have it this. So the correct answer we have to find from this option. The charge is a positive and showing down. The charge is a negative and showing down. The charge is a positive and speeding up. And the charge is a negative and speeding up. So the correct answer for this question is the charge is a negative and showing down. Moving with the next question. The next question we have, the current is from left to right in the conductor shown. The magnetic field is into the page and point S is at the higher potential than point T. The charge carries are. This is the diagram. We have options: positive, negative, neutral, and absent. The correct answer for this question is the positive. Moving with the next question, a current carrying coil is placed with its plane in the magnetic meridian of the earth. We see from the east side a clockwise current is set up in the coil. The magnetic field at its center will be directed towards north, south, west, or east. So the correct answer for this question is the west. The current carrying coil, if that will be placed in the meridian of the earth, and if we observe from the east and the current moving clockwise for that scenario, magnetic field at the center will be directed towards west. The next question we have, if we double the radius of the coil keeping the current through it unchanged, the magnetic field, its axis at very far away points become 4 times, its double, remains unchanged, or half. The correct answer for this question is it becomes 4 times. Okay, like as we saw in the formulas also, B is directly proportional to 1 by r square. So if the radius will be actually 2 times, that time magnetic field lines will become 4 times actually. Okay. A loosely wound helix made of stiff wire is mounted vertically with the lower end just touching the dish of mercury. When a current from the battery is started in the coil through the mercury, the wire oscillates, the wire continues making contact, the wire breaks contact just when the current is passed. The mercury will expand by heating due to the passes of a current. The correct answer for this question is option 1. Moving ahead, an electron of charge E moves in a circular orbit of radius r round the nucleus of the magnetic field due to orbit motion of the electron. At the site of nucleus is B. The angular velocity omega of the electron is omega is equals to mu naught EB divided by 4 pi r. Omega is equals to mu naught EB divided by pi r. Omega is equals to 4 pi rb divided by mu naught times c. And omega is equals to 2 pi rb divided by mu naught times c. The correct answer for this question is option 3rd. Next we have a question. A particle of a charge q and mass m moves in a circular orbit of radius r with the angular speed omega. The ratio of the magnitude of its magnetic moment to that of its angular moment depends on omega and q, omega q and m, q and m, omega and m. So let's try to firstly solve this particular problem. So as we know the formula from basic, like magnetic moment will be mu is equals to Ia, which is equals to qv by 2 pi r into pi r. So from basic we know already V is equals to r omega. So mu by L, that is the angular momentum, L is equals to we know mvr. So from here we can say mu by L is equals to qvr divided by 2 into mvr. Understood? So from here we can get the value q by 2m. From here we can say the correct answer for this question is q and m. Okay, like its angular moment depends on the value, as we can see on the last q and m. Okay, this is the final, which is a q and m. Now next question we have two concentric circular loop of radii r1 and r2 carrying clockwise and anti-clockwise current i1 and i2. If the center is null point, i1 by i2 must be equals to r2 by r1, r2 square by r1 square, r1 square by r2 square, and R1 by R. So let's see the firstly solution of this question. So for solution, students, we know at the center they have equal magnitude. And the magnetic field direction are opposite, as we can see over there, because of the direction of a current. So if I'm just taking the mod of these both the section, like for I1 and I2, so this will becomes mu I1 divided by 2R1 is equals to mu I2 divided by 2R2. From here we can say I1 by I2 is what come, that is comes R1 by R2. From option we can say the correct answer is R1 by R2 also. Hope you are able to get the solution. Next question we have, a charge E moves round a circle of radius r with a uniform speed v. The magnitude of a magnetic induction at the center of the circle is mu naught EV by 4 pi r, mu naught EV by 4 pi r square, mu naught EV by 4 pi r cube, and mu naught ER divided by 4 pi v. So let us see the solution part, how we will get the formula. So we know the value of a current, that is a current I is equals to delta Q by delta T. This is from basics we know. And now which is equals to EV by 2 pi R. Magnetic moment or a magnetic field, if I'm just taking magnetic field, due to loop of radius r carrying current I at the center is, we know the formula for this also, which is comes V is equals to mu naught I divided by 2R. So from here, like if we just put all these value towards here, so this will becomes like I value EV mu naught divided by 4 pi R square. So from option we can say the correct option is option 2. Okay. Moving ahead with the next question, the magnetic field at the center of the circle O due to a current through a loop as shown in the figure. So 0, perpendicular to paper inwards, perpendicular to the paper outwards, perpendicular to the paper inward if theta is less than or equals to 0, and perpendicular to the outward if theta is in 90, theta actually lies between 90 to 180, like less than 90 or equals to or greater than 90 or equals to. The correct answer is the paper perpendicular to the paper outwards. Next question we have, a coil carrying a heavy current in an anti-clockwise direction is mounted in north-south vertical plane. A small magnetic needle at its center will be its north pole in east-north direction, west-north direction, east-south direction, west-south direction. The correct answer for this question is east-north direction. Moving ahead with the next question. Next question we have, a circular coil of wire carries a current. PQ is the part of a very long wire carrying a current and passing close to the circular coil. If the direction of a current are like those shown in the figure, so then the direction of force acting on a PQ is, we have an options parallel to the PQ towards like P. Next, parallel to PQ towards Q, at right angle to PQ to the right, at right angle to PQ to the left. So if I'm just talking about the solution criteria, so we know there will be a circular coil, which is a dipole placed non-uniform field, like a due to because of P and Q. So magnetic field, now the circular coil this will be out of the plane and non-uniform. Therefore, force which will actually act between these two, that is F is equals to dl, vector dl cross vector b. So since dl is a vertically downward and b is out of the plane, so force will be towards left direction. Understood? So if the force will becomes towards the left direction, that is a perpendicular to the PQ or right angle with the PQ, we can say. So according to this, we have the correct option, which is 4. Like at the right angle to PQ to the left. Moving ahead with the next question, a conducting circular coil or loop of radius r carries a constant current I. It is placed in a uniform magnetic field B such that B is perpendicular to the plane of the loop of the magnetic force acting on the loop is. We have an options BIR, 2 pi, BIR, 0, pi, BIR. The correct answer for this question is 0. Moving ahead with the next question. If the angular momentum of an electron revolving in a circular orbit is L, then its magnetic moment is ELM, EL by M, EL divided by 2M or 0. The correct answer for this question is EL by 2M. Next question we have. If a current is passes or passed in a spring, we have an options magnetic dipole, magnetic substance, magnetic pole, non-magnetic substances. So for the correct answer, we can say that like for the two wire, if they have same direction, exert same attractive force towards each other. So for that scenario, we can say magnetic dipole scenario for that. Next, we have a current loop placed in a magnetic field behaves like a get compressed, get expanded, oscillates, or remains unchanged. The correct answer for this question is get compressed. Next question we have a circular coil of one turn and area A carrying a current has magnetic dipole moment M. The current through the coil is MA, A by M, M by A, M by A square. The correct answer for this question is M by A. Moving ahead with the next question, a magnetic dipole placed in a two perpendicular magnetic field vector B and vector B naught is in equilibrium, making an angle theta with vector B. Then B is equals to B naught, P cos theta is equals to B naught sin theta, B cos theta is equals to B naught cos theta and B is equals to B naught tan theta. The correct answer for this question is B cos theta is equals to B naught cos theta. Moving the next question. So next question we have a current carrying loop in a uniform magnetic field will be experience force only, torque only, both force and torque, and neither torque nor force. So if I'm just taking the solution criteria, when the current passes through actually the magnetic field lines cross through the loop, and for this scenario, this force ultimately turned into the torque. So the correct answer for this question is a torque only. Again, I'm just explaining this part. When the current passes through a current carrying a loop in a uniform magnetic field, I'm just explaining over there. Like when current passes through or passed through a current carrying loop. Current carrying loop in a uniform magnetic field. The magnetic field lines cross with the loop and hence it experienced a force. Okay, it experienced a force. This force ultimately turned into torque. So if I'm just taking overall, so they have only torque. This is the final solution. So I hope you get it this point. Next question we have a small coil. A small coil of n turns has an area capital E and a current I flows through it. The magnetic dipole moment of the coil will be I N A, I square N A, I N square A and I N divided by A. The correct answer for this question is a so simple question, that is the option 1. Moving ahead with the next question, a circular current carrying has a radius r. Its magnetic dipole moment is directly proportional to r square 1 by r and 1 by r square. So from the basic and from the standard knowledge also, we can say exact answer for this is just r square directly. Now the next question, an electron moves with the constant speed v along a circle of radius r. The magnetic moment will be EVR by 2 pi r square EV 2 pi r EV. The correct answer for this question is EVR by 2. Next question we have, a circular coil has one turn and carries a current I. The same wire is wound into a small coil of 4 turns and the same current is passed through it. The field at the center. We have an option decrease to 1 by 4th of the value is the same increase to 14 times the value increase to the 16 times of the value. So for the solution criteria, we know the answer, this is a 16 times of the value. Moving ahead with the question, a conducting loop carrying a current I is placed in a uniform magnetic field acting perpendicular to the plane of the coil as shown in this diagram. So the loop have tendency to, this is a diagram which is showing over there. So for the correct answer, we have an options are contract, expand, move towards positive X rays, move towards positive Y rays. So moving ahead with the solution part, like here, we use the flamings. So we use the flaming left hand rule. So in the flaming left hand rule, okay, we can easily find out the current carrying conductor. For this, as the diagram already is shown, we can calculate few more things from this section. So now in the as we can see the direction. So if I'm just taking a small element of these scenarios, so this will be if I'm just assuming DL. So the force is of F1 in this one and F2 in this. This will be again like radially outward. This will be F3 and this will be F4. We can make like this. So let us consider a small length, that is a DL, on a current carrying loop. The direction of that small length is always like tangent to the loop. So now using flaming left hand rule, we can see when the like fingers actually curled. So direction of the current will be, and the thumb is pointing towards like radially outward the direction of force. So the what it's mean, at every point on the loop, the force is acting radially outward. Actually, will be the case of a current carrying a loop. Hence, the loop will be expanded. So the correct answer for this question is expanded. Next, we have a straight wire of length L is bent into a semicircle if the current I is passed in it be at the center O semicircle. So we have these options. The correct answer for this question is option 3. Mu naught pi I divided by 2. Next, we have a circular coil of n turns has a diameter d and carries a current I. B at the center of the coil is, we have an options are these. The correct answer for this question is 2. Next question we have a circular coil carrying I suspended in a non-uniform magnetic field lines has translatory motion only, rotatory motion only, both translatory and rotatory motion, neither translatory nor rotatory motion. The correct answer for this question is both translatory and rotatory motion. Next, we have a spring is held vertically downward and a current is passes through it. The length of the spring increase, decrease, does not change, may be increase or decrease depending on the direction of flow of current. Now, the correct answer for this question is a decrease. Next, we have a current element of the length dl carries a current I. It behaves like a magnetic pole. Its pole strength varies from 0 to ideal, ideal to ideal, ideal by 2 to ideal, I square dl to 0. The correct answer for this question is 0 to ideal. Next, we have a question. A straight wire carrying current I is kept parallel to the y-axis. The direction of the magnetic field at the point P in the direction or in the xy plane is along. This is actually diagram of that question. We have an options x-axis, y-axis, z-axis and minus z-axis. The correct answer for this question is a minus z-axis. Last question we have. The force on the linear conductor, the magnetic field is half of the maximum value when it makes an angle dash with the field 30 degree, 60 degree, 45 degree, 15 degree. The correct answer for this question is a 30 degree. Now student, remaining we have a lots of a question which is attached from like this question. Remaining question we will do in the next like practice time 2 session. I hope you like this session and you get the practical knowledge also from this particular scenario. Like if we just take a spring and we change the direction of a current, it will be becomes expanded or it will be becomes like compressed. Like in this scenario, like we just get the answer like compressed. So these kind of experiment you can do in the like laboratory also. So like key skill we also like do the practice scenario. Now moving ahead, like remaining question we will do in the next session. Till that, take care everyone and thank you for watching this video.